Hi, Year 12. I hope you're all well. So as I said in my last live lesson on Teams, I was going to produce a pre-recorded lesson on the Haloalkanes topic. Now, this lesson, as I mentioned, contains nothing new. So it's not going to go into any new content. It's just going to go through some of the tasks which hopefully you've already completed in your question packs. So this is really just an opportunity for you to do some self-assessment of the work you've completed and to get some feedback and hopefully pick up some hints and tips on things you've either misunderstood or errors that you've made so you can improve and know what to do differently next time. Okay, so I'm just going to share my screen so you can see what I'm pointing at. Let me just do this. Okay, so hopefully you can all see there the Haloalkanes question pack that I'll be going through. So I'm going to go through tasks 1 to 7 and then also past paper questions number 11 and 12. Okay, so this is an opportunity for you to follow this video through whilst you've got your question pack open with you and check and amend your work as need be. Okay, I'm going to rattle through these relatively quickly, but of course you can always pause this recording and rewatch sections of it again if you need to. Okay, so starting at task 1 then. So essentially we've been given 3 different haloalkanes that we have to draw and then draw out the dipoles on them. So the delta plus and delta minus charges. So for the first one, we've got 2,2-dibromo, 1,1-dichlorobutane. Then we've got 1,2 dichloro, 1,2-dibromo propane. And you'll actually, those of you who are a bit eagle-eyed will have noticed the name here is actually incorrect. It's got chloro before bromo. So actually there is an error in the question there because really alphabetically the bromine should come first. But either way, a chlorine on 1 and 2, a bromine on 1 and 2. And again, wherever you've got a halogen, it's going to be delta minus, and the carbons that they're attached to are always going to become delta plus. 2-chloro, 2-methyl-butane, so meth, eth, prop, bute, and then on carbon 2, we've got a chlorine and we've got a methyl group. Remember, it's asked for displayed formulae, and displayed formulae show every single bond. So your CH3 group, your methyl group, has to be drawn out with all the bonds, okay? If you'd drawn it as just a CH3, you would lose the mark in an exam because it has to show every single bond, okay? Task 3, you're given some haloalkanes and we just have to state whether they're primary, secondary, or tertiary. So this first one, 1-chloro, 2-methyl-butane. So here, the chlorine's on carbon 1. The carbon that it's attached to only has 1 neighbor, so it's primary. The secondary, we've got 1-chloropropane, meth, eth, prop, chlorine's on the end, and that carbon has 1 neighbor, so that's also primary. And then the second one, 2-chloropropane, it's a 3-carbon chain with the chlorine in the middle, and the carbon that it's attached to has got neighbors on both sides. So it's got 2 neighboring carbons. So that makes that one secondary, or you could have written the shorthand as well if you'd wish. Okay, moving on. Just a bit of nomenclature. So we've got CCl2F, CClF2. I would find it when you've got a formula like that, it's always much easier to draw it out in either a skeletal or a display formula way. So essentially we've got 2 carbons in this molecule. So there's our 2 carbons. We've got 2 chlorines and a fluorine on the first one. So 2 chlorines and a fluorine. We've got 2 fluorines and a chlorine on the second one. So I'm going to call this 1,1,2-trichloro because we've got a chlorine on 1 and 1 and 2. And then 1,2,2-trifluoro, 1,2,2-trifluoroethane. Okay, now because whichever way you name this molecule, there's going to be 3 number 1s and 3 number 2s in the name. So theoretically, the numbering could go the other way around. Rather than 1,1,2-trichloro, it could be 1,2,2-trichloro and vice versa for the fluoros. So either of those are possible. The next one, we've got a molecule where there's 3 fluorines and 1 chlorine, but of course we've got to be alphabetical. So 1-chloro, 1,2,2-trifluoroethane. And then finally, we've got a molecule where we've got 3 bromines, 2 chlorines and a fluorine. And these also need to be alphabetical. So 1,1,2-tribromo, 1,2-dichloro, and then 2-fluoroethane. And remember, commas between numbers, dashes between letters and numbers. Okay, right. Moving on, so task 5, then we've got our first free radical substitution mechanism. So write the overall equation and describe the mechanism for the formation of 1-bromobutane from butane by radical substitution. So I'm going to do the overall equation in just a second, but remember we've got our initiation step where we form our bromine radicals. The first propagation step always removes a hydrogen from our alkane. So C3H8 is going to turn into C2H7, but I've drawn this as a structural formula because it wants specifically 1-bromobutane. So if we're aiming for 1-bromobutane, it has to be clear that the radical is on the end of the chain, because theoretically you could form 2-bromobutane for this. So with that in mind, the hydrogen we remove is on the end, it forms HBr. This, oh, and you know the other error actually, apologies, I've just realized it's butane and I've done propane, so I actually need to change this. C4H10, I've only done prop, CH2, CH3, so I'm a carbon short on each of those. So that means this one's a carbon short. So that radical formed starts the next propagation step where it collides with another bromine, and one of those will stick on the end. Let's just add one more carbon on the end of there, and we regenerate a bromine radical at the end there. Now, if you recall, the overall equation, the best way to get the overall equation is to add up the 2 propagation steps and cancel out any radicals. So we should have C4H10 plus Br2, because the radicals that are on this side cancel. So C4H10 and Br2 are on the left, and it's going to make HBr and our 1-bromobutane product. So Br, CH2, 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 CH3. So that's our overall equation. And then we've got 3 possible termination steps. 2 bromines, oh, I'm off the screen there. 2 bromines could pair up. Again, these radicals are now not long enough. A bromine could combine with a butyl radical to form bromobutane, which is our desired product. But also 2 butyl radicals could pair up. CH2, 1, 2, 3, 4, 5, 6, 7. So if 2 butyl radicals collide, we'll end up forming octane. So that would be our unwanted alkane byproduct as well. Okay. Next, so question 2 from this task. So chlorine reacts with methane, forming chloromethane. State and describe, with the use of suitable equations, the mechanism for this reaction. Include conditions required for the reaction to occur. So initiation, Cl2 splits up into 2 lots of Cl, and our condition is UV light. Propagation, the chlorine radical collides with the alkane and takes a hydrogen off it. So that's why we make HCl and a methyl radical. And then that methyl radical collides with another Cl2 and splits it up. One joins onto this to form chloromethane, and it regenerates another Cl radical. 3 possible terminations. So we could have 2 chlorines pairing back up. We could have a chlorine and a methyl pairing back up to make chloromethane, or 2 methyls pair up to form ethane. Overall equation, exactly the same process as before. Add up the 2 propagation steps and cancel out any radicals. So that's where we end up with methane and Cl2 forming chloromethane and HCl. A problem with this reaction, further substitution may occur, and that's always the problem with any free radical substitution. Right, number 3, we did actually go through in one of the lessons. Number 3 is a bit of an odd one, because rather than dealing with a diatomic halogen molecule, we're dealing with IBr. Now, IBr, an iodine bonded to a bromine, should still be treated just like a halogen. So if we undergo the initiation step, this is going to split up into an iodine radical and a bromine radical. So that's what this first initiation step is. Now, we've just got to be careful that because we've got 2 different halogen radicals present, there's actually a lot of different kind of outcomes of this reaction. So we got to be careful that the equations that we give lead to the products that the question is actually asking for. So the question wants iodomethane and it wants hydrogen bromide. So for that reason, the first propagation step has to involve the bromine radical, because this takes a hydrogen off our methane, sorry, and it makes the HBr product that the question wants, as well as this methyl radical. The methyl radical then reacts again, and if it collides with the IBr, we know it has to be the iodine that's going to attach onto it, because that's what the question wants. So CH3I, and it reforms a bromine radical. So those aren't the only equations that could occur inside this reaction, but they're the ones that the question is asking for, so that's why we've incorporated them. And then similarly, because the question has asked for iodomethane, I've just indicated one termination step here, iodine pairing up with a methyl radical to form iodomethane. So I've put under here lots of other possible equations depending on whether the iodine or the bromine reacts. If this was swapped for an iodine, you'd make IBr, okay? If here it wasn't iodine attached, you'd end up with bromomethane, okay? So there's lots of feasible products. We're just giving the ones that the question is asked for. Okay, moving on then. So the next questions involve the nucleophilic substitution mechanism, the curly arrow mechanism that we looked at last time. And it is really important in these exam questions that you do what the question states, okay? Almost treat the information given in the question as a tick list, because often people lose marks in questions on this topic, not because they don't know it, but they just haven't written everything that the question's asked for. So in this task 5, it says, show ethanol, how ethanol is made from a haloalkane, state the reagents and the conditions. So the first thing I'm going to do is give the reagents and conditions. So reagents, we need either sodium or potassium hydroxide, either is fine. And because we're making ethanol, we need to start off with a haloalkane with 2 carbons. So it's going to be chloroethane, but it could also be bromoethane or iodoethane. It needs to be an ethane with a halogen on. I've picked chloro, but it could be one of the others. Our condition, this has to be aqueous conditions, and you could also say warm aqueous if you want, but the key bit is aqueous. So then our curly arrow mechanism, here is our chloroethane molecule. It's got a delta minus chlorine and a delta plus carbon. The sodium or potassium hydroxide act as a source of hydroxide ions. And remember, the lone pair and negative charge needs to be on the oxygen. And we get a mark for the curly arrow from that lone pair onto the delta plus carbon. So that will get you a mark in an exam. And then the second mark, we break the carbon-chlorine bond onto the chlorine, and that swaps the hydroxide group in place of the chlorine. So they end up swapping places. Okay. Next one. So name and outline the mechanism for the production of butan-1-ol from a chloroalkane. So if we know it's butan-1-ol, we know the haloalkane we need to start off with is going to have to be bute, meth, eth, pro, bute. And if we want the ol to end up on carbon 1, it means the halogen needs to start off on carbon 1 or either end of that chain. So you could use bromobutane. I've used chlorobutane here. It doesn't make, oh no, actually it says from a chloroalkane. So you can't start off with the bromine version. You have to use the chlorine version. Okay. Now it says name and outline the mechanism. So this time we've got to name it. Nucleophilic substitution, 1 mark. Here's the correct starting material. Again, it didn't tell us to use 1-chlorobutane. It just said a chloroalkane. So we've had to work that out. Our hydroxide ion, and we have the same delta plus and delta minus charges. So a mark for attacking the slightly plus carbon, a mark for breaking the carbon-chlorine bond. And that would result in 1, 2, 3, 4 carbons with the OH attached. And the chlorine that's been kicked off floats around at the end there. Now, at this point, it's worth highlighting, in an exam, you don't necessarily get any marks for the product. If this was an exam question, I don't think you would, because it actually tells you you're aiming to make butan-1-ol. So even if you had no idea what curly arrows were going on here, you could write the structure butan-1-ol as the product and, you know, expect a mark for it. But my point is, you're not going to, because it's told you in the question that's what the product is, then it's not worth a mark. But just for completeness, I typically would still finish off a mechanism with the product that you're expecting. Okay, question 7 or task 7, the last one I'm going to go through on the tasks. Now, this is one to watch out for because I think some of you will fall for a trick here. So write a chemical equation and outline the mechanism for the production of butane nitrile. Right, so if it's butane nitrile, this is one where we need to be using our cyanide nucleophile. And it's very easy to think, right, butane nitrile, meth, eth, prop, bute. Well, if it's butane, then I need to start off with chlorobutane or bromobutane. So I'm going to start off with that. My cyanide ion, negative charge and lone pair on the carbon. I've got a delta minus on the chlorine and a delta plus on that carbon. So your curly arrows are going to follow the same routine as normal. So the cyanide group kicks out the chlorine. But hopefully a few of you are going to see or have already kind of worked out where I'm going with this one. We've not made the right product, okay? Our product has got 1, 2, 3, 4, 5 carbons. So our product is pentane nitrile. So because nitriles add an extra carbon onto the chain, if we're trying to make butane nitrile, we've actually got to start off with a haloalkane, which is 1 carbon shorter than what we want. So all of what I've just gone through is incorrect. So let's rethink. If I want butane nitrile, I need to start off with prop, meth, eth, prop. And just for variety, I'm going to start off with the bromine version, 1 bromopropane. Okay, so my cyanide ion comes along. The bromine's delta minus, the chlorine is delta plus. We attack the carbon. We break off the bromine. Those are my 3 carbons from the prop chain, but now we've got the CN group, which has taken the place of the bromine. And the bromide ion is kicked off to do its own thing. So now we have made butane nitrile because we've got meth, eth, prop, bute. We've got that correct number of carbons, okay? So it says write out the chemical equation and outline the mechanism. So we've done the mechanism. Let's do the equation. Let's do CH3, CH2, CH2Br plus CN minus, and again, negative charge lone pair on the carbon, is going to go to CH3, CH2, CH2, CN plus Br minus. Okay, so that would get you the mark for the equation. Alternatively, though, for your equation, rather than putting CN minus, you could put the reagent. So if you remember, the cyanide nucleophile can come from potassium cyanide. So rather than writing CN minus, I could put KCN, which is absolutely fine. I just need to remember that in my product, rather than kicking off a bromide ion, I would make KBr, potassium bromide. Or you could even write that out as K plus and Br minus, because in reality, they would be dissociated into their separate ions because it would be in solution, okay? So either of those are correct versions of the balanced chemical equation for that process. Okay, so that's tasks 1 to 7 that I've gone through there. And I'm just going to jump now and go through past paper questions numbers 11 and 12. Okay, so past paper question 11. So the equation below represents a reaction between methane and chlorine, and it's given us the balanced equation here. State an essential condition required for the reaction to occur. Explain why this condition is essential. So we have to have UV light. Gets you a mark. Why? Because it provides the energy to break the chlorine to chlorine bond. UV light is higher energy light than regular white light. Okay, that's why you got to worry about getting sunburn with the UV light. So it's the energy from UV light that provides enough energy to break that chlorine to chlorine bond. State the type of mechanism. It's a free radical substitution. State or name the 3 types of steps. So initiation, propagation, termination. That should all be fairly routine to you by now. Right, a few more complex questions then. So in addition to CH3Cl, in addition to chloromethane, compounds such as dichloromethane and chloroethane may also be formed when chlorine reacts with methane. Write equations for the 2 steps in the mechanism by which CH2Cl2, so dichloromethane, is formed from chloromethane. So hopefully you are thinking at the moment further substitution. Okay, so we're aiming to make methane, but the question is telling us you might actually end up with some dichloromethane. So how's that going to happen? Well, let's imagine that some of the chloromethane that we've made collides with another radical. So we're essentially going to go through 2 more propagation steps here. So this chlorine radical removes the hydrogen. So we're going to end up with HCl and CH2Cl. This chloromethyl radical, the second propagation step, it always involves colliding with another diatomic halogen molecule. So if this splits up and one joins onto here, we're going to end up with CH2Cl2, and we're going to regenerate our chlorine radical. So by going through those propagation steps a second time, we're making that dichloromethane product. Okay. And then finally, another kind of link to further substitution. It says, write an equation to represent a step in the mechanism in which chloroethane is formed. Right, well, if we go back and visit our further substitution that we just went through, this process involves making what we call chloromethyl radicals. But, let me just jot that down. Chloromethyl radicals could easily come into contact with regular methyl radicals that are made in the first round of the reaction. So there will still be some CH3s floating around in that mixture. So it's quite feasible that a methyl and a chloromethyl radical could undergo a termination step together. And we end up making chloroethane, which is what we got here. Now, that isn't the only answer to that question, but it's certainly the most logical answer, the one that I'd be expecting you to come up with. Right, final bit then, past paper question number 12. So chloromethanes, such as dichloromethane and trichloromethane, are produced in industry as they have many uses. Trichloromethane has been used in the manufacture of the refrigerant chlorodifluoromethane. At the moment, all of that, they're just telling a bit of a story. It's fairly irrelevant. They're just trying to add a bit of context to the question. Let's actually get on to what they want us to do. We're told chlorine reacts with dichloromethane to form trichloromethane. Write an equation for each of the following steps in the mechanism for this. So, initiation step. Well, if we're talking about chlorine reacting, the initiation step is same as normal. Cl2 splits up into 2 chlorine radicals. Now, if we're talking about dichloromethane forming trichloromethane, we need to start off with dichloromethane here. So CH2Cl2. It collides with a chlorine radical. And remember, the first propagation step, the chlorine always takes a hydrogen off our alkane. So we're going to form HCl, and that will leave us with CHCl2, a dichloromethane radical. So this starts off our next propagation step, CHCl2. And remember, the second propagation step always involves colliding with a newly reformed diatomic halogen. So these two will collide, the chlorine will split up, one will add on to it. So we end up with CHCl3. And therefore, the chlorine is reformed. But in doing so, we've made that trichloromethane, which is what the question wanted us to make. Finally, again, give one essential condition for this type of reaction and name the type of mechanism. So essential condition, UV light, type of mechanism, free radical substitution. Okay, right, so that concludes those questions which I asked you to complete. So that concludes the review of those. Having watched this video, I'm just going to stop sharing for a second. Having watched this video, I'm hopeful that that's clarified any issues or any errors that you made during that work. If you do have any further questions, you're welcome to email me. Or if you think there's something that you're stuck on which might be useful for lots of people, if you email me, and I could maybe even start off our next online lesson on Wednesday addressing any of those concerns. Okay, right. Thank you very much for watching this. I hope you have a lovely weekend, and I will see you. I'll see you back on a screen soon, but it's also not a million miles away before you're back in school, back face-to-face lessons, which is only going to be a good thing as well. Okay, right. Take care. See you soon.